Hi everyone, today I want to talk to you about logistic growth. So in logistic growth, we care about two properties. We want the rate of change of the population or the amount that we're studying. We want the rate of change to be proportional to the size of the population, and we also want the population to become stagnant at some point. That means as the population approaches a specific size, we want the rate of change of the population to become almost zero or to approach zero, okay? Now we can capture those two ideas with a very useful and pretty simple differential equation. So first, I'm going to say we have a population P, and the rate of change of this population with respect to time, but this could be really dy dx or any quantity with respect to any quantity. I'm just going to use this notation. dp dt, the rate of our population, is going to be proportional to the size of our population, so that is going to be kp, and we also want to make it so that dp dt is zero as we approach a maximum number. And we can represent that idea like this. We can say that m, the maximum, minus p times this amount. Now notice that if p is equal to the maximum, the derivative of p with respect to time is zero. Meaning when you reach p, when p reaches n, dp dt will be zero, so p, the size of the population, will stop changing. Now, it would be really awesome if we could solve this differential equation, and of course we can. So let's do it. So you can see that this is an autonomous differential equation, and we can solve it using separation of variables, which is awesome. So I'm gonna do this. I'm actually gonna switch to blue now. So we can write dp divided by p times m minus p is equal to, and we can move dt to the right hand side of the equation by multiplying, is equal to k times dt, all right? So this is what we have. Now we can integrate both sides as we usually do. So we integrate both sides, and we know the right hand side is going to be very simple. It's going to be k times t plus a constant of integration. And now the left hand side may be more difficult, however, hopefully you can identify that you can solve this integral by using partial fractions. So I'm gonna say that we can split this expression like this. We can say that 1 over p times m minus p is gonna be some constant, let's call it a, divided by p, plus some other constant b divided by m minus p. Now we're gonna use the cover-up method. So let's say we multiply both sides of the equation by m minus p. So this goes away and this goes away. Now, how can we make the a term go to zero? Well, if we let p be equal to m, the a term goes to zero, and we're gonna have that b is equal to. So we cover up this. We multiply by m over p. So we have this term. This term vanishes. And then we have 1 over m, because we let p be equal to m. We have 1 over m. That is the value of b. Now what about the value of a? Well, we do the same thing. We multiply both sides of the equation by p. We cover up p and p here. And then how can we make the b term be equal to 0? Well, we can let p be equal to 0. If we let p be equal to 0, the left hand side of the equation becomes 1 over m. So it turns out that a is also equal to 1 over m. So these are the constants that we have. Now, I'm going to continue down here. So we can write this integral like this. We can say we have the integral of let's say dp divided by m times p. So this part here is a over p plus the integral of dp divided by, and now we have b. So that should be 1 over m times this amount, or actually m times this amount. So this is m times m minus p, okay? This is what we have. Now let's continue solving this. So this should be 1 over m ln of the population. Now, the population cannot be 0 in this case. It wouldn't make sense to have minus a million humans or minus a million rabbits. So let's just say I'm not going to use an absolute value because we're assuming that the population is always positive. So this is 1 over n times ln of p, and then we have Notice here we have a negative in front of the p. We're gonna have to, if you have, this would be ln of n minus p, and if you differentiate that amount, you're gonna get a negative in front. So we have to put a negative here to cancel out that negative. And we have minus 1 over m times the ln of, and I'm gonna put absolute value here, although technically m should always be greater than p, at least in the context that I described. So really the absolute value is not necessary in this context either. So we have the ln of m minus p. So this is what we have. Now we know this is equal to k times t. So I'm gonna actually, I don't want to go too far right. So we know this amount, this expression is equal to k times t. Notice we have an m, a common factor of 1 over m. I'm going to move the m to the right hand side, and we're going to get the following expression. We're going to have ln of p minus ln of m minus p is equal to, and move m to the right hand side. So we have k times n t plus c. Okay, so I'm going to say that c, the constant of integration, absorbs this m. Okay, because it's any constant, so it just absorbs it. Now there's a really great property that we can use here. I hope that you remember that if you're subtracting two ln's, that's the same as dividing the amounts that you have inside each logarithm. So I'm going to multiply by -1 so that we can do the following. If I multiply by -1 both sides of the equation, we have ln of m minus p minus ln of p is equal to c. Again, the c absorbs the negative, k and t. Okay? Now we can write this part like this. We can say this is equal to ln of m minus p divided by p. Okay? So this is what we have. And this is great because we can now exponentiate and we get something really nice. So if we exponentiate both sides, we're going to get the following. So on the left, we're going to have e to the c, and then we have e to the minus k m t. All right. And then we have on the right m minus p divided by p. Now I'm going to say that e to the c is just some constant. So I'm actually going to erase this and just call this, let's use the letter a, okay? A, this is another a, don't think about this a here. This is just another a, another constant. Now, the only thing we have to do now is solve for p. And we can do that like this. We can rewrite this as m over p minus 1. That is why I multiplied by -1 here, so that I would be able to divide the binomial by this p and then get this 1, which is going to be really useful. And we're going to have, I'm going to move the 1 to the left side of the equation, and we have 1 plus a times e to the minus k m times t, and this is equal to m divided by p. Okay? And we just need to solve for p, so we get that p is equal to m divided by 1 plus a e to the minus k m t. Okay, sweet. Now this is, maybe you can notice, this is the logistic growth equation. This is our logistic growth function, and that's what we expected. We wanted to go from this differential equation to this. Okay, and this equation, you can see that as t approaches infinity, this term will vanish, and you're going to have n divided by 1, and that's what we wanted. We wanted to have a maximum for our population. As time progresses, we want our population to reach a maximum and stop changing, which is what the 0, this is a function that has a 0 at p equals m, and that's why dp/dt is 0. And that is consistent, that idea is consistent with this result that we just obtained. Now, we can also treat this as an initial value problem, and we can say, well, what happens if at p equals 0 we have an initial population p naught? That's something we could totally do, and let's see what that would give us for our constant. Let's see what that would give us for our constant of integration a. So I'm going to say that p naught is equal to m divided by 1 plus a. Now, t equals 0 is gonna mean that it means that e to the 0, that's 1. So then we just have m divided by 1 plus a. And we want to solve for a, that is very easy. We can do p naught. P naught, so yeah, I'm gonna write out the entire thing. I'm gonna multiply both sides of the equation by 1 over a. Then I'm going to distribute p naught P naught times a equals m. And now we can solve for a by doing the following. So we can say p naught times a is equal to m minus p naught, which means that a is equal to, and I'm going to divide by p naught on both sides of the equation. And this is our initial value. This is our value for a, so that we can accommodate an initial population. So if you want to write this in a better way, we would have m divided by 1 plus, and then this is a little big, but m divided by p naught minus 1 times e to the minus k times m times t. Okay, I hope you can see it from there. But yes, this is what we get, and this is what we would get from this differential equation. Again, this differential equation satisfies two very important properties. At m, the population stops changing, and the population growth rate is proportional to the population size. So I hope you learned something from this video, and I hope I will see you in the following video. Bye.